Good morning, all. Um, Welcome back to PSM 150X, and we are continuing with energy. I'm glad those the two students who are attending that you are here today. I don't know where the rest quite worried about the attendance. Honestly, not sure what is the case. I don't know if they're actually watching the lectures afterwards. I can always check, but I mean, obviously this will reflect um, when the tests are coming up that they did not practice at all. But nevertheless, we are here to learn. Okay, so where we are now, let me just crack my textbook open here for you. We are looking at the conservation of energy, right? Um, Things are looking good so far, but next week we'll be done with this chapter. It's a very important chapter. Um, so I'll urge you to make sure you focus on it coming in your final, coming in your upcoming test so far. So you already know in your next test, you're getting two body systems in terms of forces, and then you're getting topic 5. That was probably topic 7 and a hint of topic 8 as well, I'm sure, which we will cover. Okay, so what is this all about? I'm sure you guys are familiar with the conservation of energy, but just quickly talking to it. Um, There we go. So obviously we discussed in the previous lectures the concept of work, what is work done, which forces are important when you're concerning the work. We also looked at the kinetic energy. Then we looked at the work energy theorem, where we found that work is equal to the change in kinetic energy. And on Tuesday we looked at the gravitational potential energy. In fact, what we learned from that is it's also could be called gravitational work. So in essence, it is gravitational work. Um, Briefly had a look at obviously there's a cos zero, so therefore you need to basically mgy or mgh or mgy as we know it. And then also we looked at putting the reference levels at different set points to basically calculate the potential energy of a body. In this case, it was a skier. I'm not sure what it was, but yeah. All right. Nevertheless, um, we will be embarking to the next thing. So let me just quickly get this spot right. How can I get the mouse to move? Okay, there we go. So just reading off the slide here, it says when a physical quantity is conserved, the numeric value of a quantity remains the same throughout the physical process. So what this essentially means is that um, at the initial state, if you were at, for instance, 500 joules, in the final state, it's also going to be 500 joules, right? So it's just that the 500 joules might be split up into various components. Maybe in the first case, in the initial case, there was a lot of potential energy and some kinetic energy. Eventually, the energy has transferred from the potential to kinetic. So in the second stage, you have a little potential and more kinetic. Um, Obviously, this is talking to conservative forces, as you mentioned, and to not conservative ones. All right, so quickly reading again here. They're saying if you were to imagine the kinetic energy of an object falling under the influence of gravity, right, is constantly changing, as is the gravitational potential energy. So if you were to imagine a ball falling, initially at initial height, it had a certain amount of potential energy, and as the ball is falling, it's converting all its potential energy into all its gravitational potential energy into kinetic energy. So obviously, then these quantities are conserved because we assume that all the non-conservative forces are absent, right? That's why we obviously can do that, and we can set basically our non-conservative work equal to 0. So if we do that we will end up with this equation. So we will have the change in kinetic energy, obviously the final one's initial, plus the changing potential energy. And in essence, what we are saying is that the total mechanical energy is essentially conserved. So, long story short, this is what we're going to be looking at for today. And then, yeah, they're saying the sum of the kinetic energy and gravitational potential energy remains constant at all times. It is a conserved quantity. So, this is what we're looking at today. And then afterwards, we'll be looking at, I'll show you now, the spring potential energy. Okay. So, as an example, so let's imagine you're tossing a rock off the side of the building, right? So we obviously ignore any non-conservative forces like drag forces, air friction, etc., etc. So as the rock falls, right, its speed increases, right? As the rock approaches the ground, the potential of the rock energy decreases. So whatever potential energy is lost as the rock is moving down, it appears as a kinetic energy. And our equation says that in the absence of non-conservative forces, like I just mentioned, like air drag, friction, things like that, the trading of energy is exactly even. So this is true for all conservative forces, not just gravity. And we assume in any, and basically it's an isolated system. So we're saying in any isolated system of objects interacting only through conservative forces, the total mechanical energy of the system remains the same at all times, which is very important. So long story short, um, the stone had initial velocity plus its initial potential energy, and we basically equal that to its final kinetic energy plus its final potential energy. So I'm sure we all familiar with this. And just important to note here is that this form of the equation is particularly useful for solving problems explicitly in solving one of the mass and gravity. And in that special case, where you will see fairly often, you'll notice that the mass will always typically cancel out with this because it's the same object and there's the same mass. Moreover, keep in mind, though, that it is possible only, only because of any change in kinetic energy of the Earth in response to the gravity field of the object M has been neglected, rightfully so. So in general, there must be a kinetic energy terms for each object in the system and a gravitational potential energy terms for each pair of objects. So obviously, we kind of know that. In other terms have to be added when conservative force are present. But we will see that as we embark the problem. Is there any questions? Are we familiar with the conservation of mechanical energy? Right? I know you guys did this briefly in matric. Is that correct? Yes or no? I'm a Charlie Gift. Okushe. Any questions, guys? Before I solve the first example. Sandile, Namnebo, Colin, any questions? Okay, thank you. Guys, you can talk. If you don't understand, you can ask, please. Lawrence, good morning. Okay, perfect. Gift. Oh yeah, that's the cancelling of the masses. Yeah, basically you can remove the masses. I'm just waiting on gift. Oh, okay, cool. No stress. All right. So there is a thing pen share. Not gonna bother too much about that now because you're rather get into the problems, very important problems. So just the problem solving strategy. I normally don't mention this, but obviously we define the system assuming it's an isolated system, and therefore there's basically the absence of non-conservative forces, right? That's the first thing. We choose location Y, and why is that important? So obviously the reference point for the gravitational potential energy. We select a body of interest. Obviously, it's typically given in the problem, and then we identify the 2 points, which is essentially the initial and final point. And then we write down the conservation of energy equation. We identify all energy forms, potential energy, kinetic energy. Sometimes it's work done to friction, sometimes it's work done. Obviously, we have to identify the unknown quantity and then solve the unknown quantity, which is either a speed or a position. Yes, gift. You're raising your hand again. Was that a mistake? Is that a mistake? Yeah, okay, cool. So yeah, that's basically all. And eventually we're going to spring. So let's obviously start on our, I might have 3 examples here. And I like to say again, I'm assuming you're practicing. Why is my whiteboard opening now? And if you have any problems, always reach out to the tutors, or anything crazy, just email me. But I think you're well equipped to solve most of these problems. Right? So make sure you're practicing every day. That goes without saying. Tomorrow is Friday, so I assume you can put in a good 2 hours there. Okay, let's quickly I'm just getting the whiteboard ready here, guys. Just give me a second. And then we can commence. So guys, just 2 minutes. And you can just prepare your books and calculators. I'm just gonna get the question out. So I'm hoping to do at least 3 questions here. Maybe 4. We can find some nice ones. And then we can go to the spring. And then we're basically done for the day. Yeah. So energy has a lot of subcomponents. So yeah, it's a bit of work. A lot of different types of problems in this particular thing. But just give me a second. Still, okay, here we go. Let's open up. And all of this is going to nicely help you next year. But make sure you understand the concepts, the analysis, and yeah. Okay. So we're doing example 5.5. Why isn't my snipping tool working actually? Okay, example 5.5. And that's on page 136 of the textbook. Okay. Cool. So here we go. Hope you guys can all see that. Just share my. Just lock it. Okay. So 136. Cool. I think everyone can see this. So again, we just essentially the conservation of mechanical energy to calculate a few things. In this case, the speed of the body. So a diver mass M drops from about 10 meters above the water surface. I think we can all imagine that. Let's assume who can I assume it is? Singalaka. Is jumping from the board. And obviously, when you neglect air resistance, which is a non-conservative part, right? Because obviously there is air friction. Use the conservation of mechanical energy to find speed 5 meters above the water surface. And then also B, find his speed as soon as he hits the water. So right, so obviously we set the initial part at 0. So we obviously always, that's always the obvious step to do. We know that y0 here, can we call it, not what y is essentially 0, or we can call where it's going to fall down to 0, so we can set this at 0 at the water surface. All right. And obviously, because we're going from here, y will be 10 over here. Okay, so y is 10. All right. So just engaging with you guys now. So the initial will obviously be on top and the bottom. So we always now write it like this: half mv squared initial plus mghi initial, and that's going to be equal to half mv squared final plus mg. Why am I calling it h? It's y final. I'm so used to h, but just call it y. Okay, so obviously we know the mass. It's the same for all, so we can actually just remove the mass. So I'll do that now for you. By mass. It's quite strange. It's not erasing. I honestly have no idea. Okay. There we go. Remove the mass. Alright, so we just essentially have gravity and that over there. So tell me at the first point, right, when it's on the tire board, does he possess any kinetic energy? What is his speed? Do we know? And also, it's important to note to be at 5 meters now, right? So we're only finding it at this particular portion of here. So this is our speed of interest. So at the first point, does he possess any kinetic energy? Yes or no? I'm waiting on you guys. What energy does he possess? Does he possess kinetic energy? Does he possess potential energy? Precious? Stanton? Or Kuhle? Lufefe? What energy does he possess at on top of the dipole? The question is, what energy does he possess on the top there, on there when he's diving? Does he possess kinetic energy? None. Gift is completely wrong. He only has potential energy. That is correct. So what it means is that this guy is gone. So we only have G times Y1. Obviously, when you get in the mass, in this case, we have 9,81 times 10, right? That equals. Now my question is, at where are we now? Over here, right? So we require to find his velocity over here. Does it possess kinetic energy and does it possess potential energy at this point here at 5 meters? At 5 meters, does it possess kinetic energy and does it possess potential energy at the 5 meter mark? You guys get the question? Yes, she's right. Both, exactly. So what we then should do, I'm just doing my calculation here quickly. It's both, right? Okay. Um, why isn't my answer corresponding here? Oh, I'm looking at the wrong sheet, sorry. Yeah. Okay. So what we then do now, we know the positions both, so that's half VF squared plus 9,8 and we times this by 5. And again, the only reason why we remove the mass was because it's the same body we're looking at. Sometimes you can have two bodies, and therefore we have to account for each body's kinetic energy and potential energy. So in this case, we have 9,8 or 9,81. I just call it 981 in this case. It's 10 minus 5. Right, so I'm just carrying over that term to this side. We're left with a half v squared, the final. And I'll just quickly work out that one for you. So you get 49,05 half v squared. And obviously divide that by 0.5, you get 98. Essentially double that value. And obviously we're just going to root that. So we can do the maths, and you end up with VF being 9.90 meters per second. Is that clear to everyone? Can we all do this? This part A. Can we all do this one? Is there any questions with this particular problem? Just check the house. Thank you, Stanton. Stanton says no. Guys, please ask questions you're unsure. Zandile, Nomlebo, Mtobisi, Kiara, Kwanele, Tabo. I told you second semester, you're working. Any questions, guys? Stanton says no. So if not, I want you guys to do B for me. B is when you have to find your speed now at this point over here now. Right? So when he hits the water. So can you guys quickly do that? Can you explain the last part, so from 10 to 5. From 10 to 5, where is that? Oh, this okay, all I'm doing is this. I'm bringing over this part, this over here, to that side, to the left-hand side of the equation. I'm just taking a common factor of 9,81. I just use 9,81 as the gravitational. I could use 9,8. So you have 10 minus 5. I'll just further explain it here. I'm just saying 9,81 times 10 minus 9,81 times 5. I'm just bringing over this term to the left-hand side. Is that clear? Any other questions? Any other questions? Okay, perfect. So I'm just going to do the analysis part, and you guys can do the solving part. So On top, we've agreed that he has no kinetic energy. So I'll write it out again anyway. We have YG1. We have half VF squared plus GY2. Right? So we agree that at the first point, right, over here, he has no kinetic energy. He possesses potential energy. Right? And then over here, he has what you're looking for, the wanted speed. So at the bottom, he possesses kinetic energy, obviously. But I have to ask you, at when he hits the water, does he have any potential energy? Yes or no? No, thank you very much. Right? Okay. So let's just we can remove this guy. So the only two unknowns is GY1 and a half VF squared. All right. So you guys can do the math for me and work out the final velocity. Yeah, and work out the final velocity for me. Is it all clear, students? Should be easy, right? Fantastic. 14. Yep. Well done, guys. Well done. Well done. All right, that is quite easy. I'll give you one more. With this one, yeah, you'll see it now. This is nice, cool one. You guys can do this one, then I'll just talk towards the end of it, right? So same principles, nothing has changed. So analysis is just to identify, you know, the potential and kinetic energies. So in this question, you could imagine cricket if you'd like to decolonize this problem. For our context, I hope you guys can all see this. This one is for you. So in the bottom of the ninth inning, a player hits a 0.15 baseball cricket ball over the outfield fence. The ball leaves a bat with a speed of 36 meters per second, and a fan in the bleachers, or in the, I'm assuming that's the where they're sitting, catches it at 7.2 meters above the point where it was hit. Right? Assuming frictional force can be ignored again, the non-conservative part is ignored. Find the kinetic energy of the ball when it's caught. So that's at point F. and I also want the speed when it's caught. All right. So, and then in this case, I want the kinetic energy, right? So this one is quite interesting. So yeah, it's the same thing essentially. But let's see. Is it clear to everyone on how to find it? Okay, we're gonna try anyway, right? So I'll give you guys the 10 parts to solve it. Is our objective clear, students? Perfect. Okay, give it a shot. Are you guys winning? You guys, pressure's got 31.71. It should be 34, at least around 34. Yeah, there we go, 33.39. Yeah, that's looking good. You guys need more time? You still want to try more? Hey, yeah, no worries. I'll explain now. Okay, so let's quickly see. So at the first point, the point I, right? Oh, it's initial and final. We've got mghi. I'll just call the kinetic energy here, vi squared. And we have mghi f plus half mv of f. Okay, so I'm assuming we all can see that. What's important here again, it's the same mass, so you can neglect it, but in this case, they are looking for the kinetic energy, right? So over here, because it's starting over here, that's the initial part. We assume what it means is that the ball doesn't possess any kinetic energy, sorry, potential energy, but it does state that it leaves with a speed of 36, therefore possesses kinetic energy. Over here, what they're asking the kinetic energy of the ball when it's caught. So it's essentially this term which we're looking for. And when it's caught, it's 7.2 meters high. So it does possess potential energy over there. So what we're essentially going to be doing is taking this part, minusing that part. So it's going to be half times 0.15 times 36 squared. That equals 0.15 times 9,8 times 7.2, and this will be the kinetic energy in the final thing. So can you just quickly work that out for me and see what you get? Are you guys following? Is there any questions with that? Ms. Charlie, are you understanding what's going on? And so Mr. Mulu and Annette, you got it? So let's just quickly work at the kinetic energy final. It's not too crazy actually. Okay, it's quite simple there. Can you perhaps tell us where you were lost maybe? But anyway, so long work the kinetic energy so long. And once you got it, you can just tell us. Let me check on who's in the house here. Ms. Bierkes, are you following? Ms. Nomebo, Zandile, Mtobisi, Nulufefe, Mtutuzeli. You guys all, are you guys with us? Sir, we use, oh, so sir, we use a mass this time. How is this different? Remember, they're asking for the kinetic energy, Ms. Charlie, in this case. So that's why we're using the mass. Because if I had to neglect the mass, I wouldn't have got the kinetic energy term. So they're asking for the kinetic energy of the ball. Yeah, there we go. When they're not asking for the speed, they're asking for the kinetic energy. That's all. The actual value. So we get 86.16 joules. Yeah. I hope that's clear, Ms. Charlie. I'm hoping, yeah. Okay, anyway. Yeah, that's why. They want the actual whole term now in this case. Is everyone happy with kinetic energy? The ones who were lost? Okay. Perfect. So obviously, once we have the kinetic energy, they're asking what its speed when it's caught. So it's caught over there. So all we have to basically do is use the final kinetic energy and put in half mvf squared, and then obviously you just have to solve for vf over here. All right. I'll do it for you here. It's 86.16 equals half times the mass, which is 0.15 times vf. So guys, what's important of this is to be able to identify where the body has potential energy and where the body has kinetic energy, set up the formula and see what's your unknown and then solve for that. That's very important here. And obviously understanding what they're looking for. But anyway, you can solve for the final speed there. You guys get the final speed. Perfect. All right. So can I ask you what confused you there exactly? Did you guys cover this in Matric? I'm sure you guys did, right? Stanton, Zizonke, Precious. If you guys are, I don't remember, sir. Oh, COVID, eh? Okay, that's why you're here. But if there's any questions, just you can ask now. We're gonna do the next example. But if you could, please send me at least 3 to 5 thumbs up, so we can move on to the next part. Thank you. Thank you. Do you want me to move on to the next part, or do you want a similar question like this before we move on? I just want to ask you, do you want to do one more practice one, and then we can go on to the last part, or oh, I wanted to ask why ignore mass, because the mass was the same in that case, and I'm looking for the speed. They didn't ask for the quantity of kinetic energy, Mr. Kowe. Kowe. I'm not sure how to pronounce that. I can give you one more problem like this, a quick one, or we can move on to this next part. Actually, Springs will probably do next on Monday. I overestimated. Okay, just some insight to this particular problem. I just want to show you how the energy is essentially converted via a histogram or bar graph. So it's quite interesting to note. I'll place it over here. For this particular problem, initially we started with no potential energy, but now around 97 kilojoules of kinetic energy. And then what essentially happens, we convert this amount to 11 joules of kinetic energy, I mean to potential energy, and then we have around 86 joules of kinetic energy. So this is just a histogram is also a nice way to obviously illustrate how the energies are transferring between two particular points. Yeah, and sometimes it gets quite involved. If you're looking at a particular body, you can actually see where all the energy is now being transferred, and where we can actually harvest whatever energy we need at a particular point. So that's just some extra insight there. Okay, I guess you guys are good. And then we're just gonna do the next example, and then you guys can obviously do the exercise at home, and then yeah. So on this one, we'll be basically using the conservation of energy to basically find the non-conservative force, which is essentially the friction part here, right? So this is example 5.7 in the textbook. You're gonna have to do exercise 5.7 for homework. And what it essentially is, okay, there's a picture here. So let me just put the picture. Not sure why they didn't make a normal sketch. Oh, there we go. It's this one. And what's happening here is that we are using the work energy theorem with the gravitational potential energy to calculate the work done by non-conservative force, which is essentially the friction. So what they say there, water slides, which are nearly frictionless, can provide bored students with a high-speed throw. So right, I'm sure you guys will know what a water slide is. One such slide, the Suker, named for the terrifying German dive bombs of World War II, is around 21.9 meters high, which is quite high, and is found in the Six Flags in Dallas, Texas, and Wetwald in Orlando. So it's essential water slide. I'm sure you've seen what a water slide looks like. You know, if you go to these pools and stuff during the holidays, you know, you can go down the slide with water, and you can basically end off of going to a pool. So in this case, what they're asking is determine the speed of a 60 kilogram at the bottom of such a slide, assuming no friction is present. So in this case, there is no friction first. So they want the speed, right? So let me just get this right. So we apply the same principle again of half mv. I don't know if we can we all envision this problem. So just imagine a slide like this. So some over here, then they're going down the slide, and they're ending up obviously something like that. I hope you all get that. So on the top you have half mv I squared, right? Plus we have our mg, keep on writing mg that. Then we have half mvf squared plus mgy2, right? So the first thing is first, you have to look at what energies are possessed. So at the top, we have no kinetic energy because she's standing still. Obviously, at the top, we have potential energy. I'm sure you agree with me. And at the bottom of the slide, she has no potential energy. So obviously, we're assuming this is zero. I mean, we all should know this by now. So saying y0 over there, and we're only left with two terms here, right? So we have this term and this over here. So in this case, no friction is present. So we know the mass was 60. You can actually cancel the masses now if you want, but I'll just keep it there for the ease sake. 9,8. The slide is 21.9 meters high. We have half, and the mass is again 60. So obviously you can see we can cancel out the 60s already if you want. And we're looking for VF squared. Is this clear to everyone? What I just did here? Potential energy. I'm just putting across kinetic energy. Yes. Can we all see this? Okay. Stanton and Kiara says yes. Yes, thank you, Mr. Kowe. Joseph, Lawrence, Punani, Precious, Sanile. Is it all clear to everyone? Perfect. Thank you. Okay, so you can solve for VF for me. Yeah. Alrighty, guys, this is our last example, and then you'll be embarking on some nice homework. And please don't go rest. Please make sure you practice what you've learned so far. By God's grace, I hope you're done with energy next week. No, we will be done, I'm sure. Yeah. Unless I extend this particular part I'm seeing here. Okay. 20.72, I'm content with that. Fantastic, right? Now, this was with no conservative forces present. Sometimes we have to obviously look at when it is present. So now in this case, if the woman clocked at 18 meters per second at the bottom of the slide, find the work done on the woman by friction, right? So that's very important. We're assuming now there is friction, and obviously the friction is making a slide from basically from top to the bottom. So just this is for A, all these sketches for B, and over here kinetic energy is present, potential energy is not present. Sorry, it's clocked at the bottom, so it's not present here. This is okay, yeah. Potential energy is present again. no, not present, sorry, confusion 2, and the kinetic energy is present, I think. So if you recall that formula, to find the work done, and what I stated to you was that the work done is a change in potential, in the change in kinetic energy minus a change in potential energy, right, which is this. So every time you have an energy problem, and I want to say it quite clearly to you, every time you have an energy problem, right, you're definitely going to be required to energy problem where you're looking at friction. This is the approach you're going to have to take. So what I mean now is that you're going to have to compute. This is not what I'm looking for. Is it right for you? You're first going to have to get the change in. Yeah, it's this. You're going to have to use this formulation over here, where you have to find the final kinetic energy minus this plus that equals this. And what's important to note of this part, and I'm going to say it now, is that remember work is also equal to your kinetic friction times the distance traveled. So there's a very important relationship. I want you to remember this one. Because there are times they're going to ask how much force, well, what was the distance traveled? So if you can compute the kinetic energies and potential energies, you're able to find the work. And if you can find the work of the non-conservative force, you're then able to find the force and the distance traveled. I hope that's clear to everyone. But in this case, I want us to find this non-conservative work, which is the friction work. Is that clear to everyone? What I just said? Bonani, was it clear? Zandire? So I'll say it again. So when they're asking to find work done by friction, we typically have to find the change in kinetic energies plus the change in potential energies, and then we find the work done. But that same work done can be equated to the frictional force times the delta x. And if you can recall, the total work done is the product of the conservative forces and the non-conservative forces, right? So I'm just making you aware on how to do that. So what I expect here now, I want you guys to calculate the work done, and it's quite easy. Just to find the kinetic energy minus the initial, which obviously in this case it's 0 on this end. And on this end over here, the final is 0, and we have the potential energy. So we're just minusing the final, minus the final, then you'll get that answer. So let's quickly calculate the conservative work. I'm not sure that's the right answer. Standards are even fire. Guys, we should ask what coffee is drinking. Is it right? Yep. Is it a positive or negative though? It should be negative if it's friction. Standard. Is it a positive or negative answer? That should be, I don't think that's correct. I think you missed something. Remember the speed changed to 18 meters per second? So let me set it up for you here. So the final we have, so that's just going to be half. The mass was 60 times 18 squared. We know that this is 0, right? There's no, oh, my bad. Yeah, in 0 at that end. Plus potential energy final. We know that's 0. And we're minusing now, what is this called now? The potential energy in the top, which is going to be 60 times 9,8 times that height, which was 21.9, I believe. All right, so all you have to do is take that term minus that term, and we should get our non-conservative work, which is essentially our friction work in this case. So are we all clear with this? All right, so let's get Yep, that's exactly -13170.34. I'm content with that answer. You all get it? This must be negative because it's friction. 0.34. Yep. That's correct. Did we all get this? Fantastic. So now my next question is, what is the force of friction, the frictional force? What is the frictional force if the woman traveled, I'm going to say 15 meters down the slide? What's the answer? What is the frictional force if the woman traveled 50 meters down the slide? Let's see who's ready to go to first the next year. Yep, fantastic. You got it. Don't forget to put newtons there. Nice, nice. Well done, guys. So, as we conclude today's lecture, I just want to give you one problem to work through, and we will tackle this problem as soon as we go on Monday, because you'll start on spring force. Make sure you do this exercise. I'm interested to see if you can solve it. Stanton or Kiara, please remind me, or Ms. Charlie, to solve this one over here. Make sure you go over example 5.8 as well. I'm quite interested to see. I'm not going to go over this one. You guys can do that. Yeah, so make sure you do this homework, which someone's going to remind me, I'll do it. And this one over here as well. And obviously at the back of your textbook. Guys, for this section, again, the name of the game for this first part is obviously to identify what is potential energy at one state and kinetic energy and what is the other, and basically just solve. And if they ask you to find the frictional work, it's quite easy. We have to just basically equate this formula, which will equal that over there. It's really, really not difficult. Another way of looking at it also is just this. We did touch on this, or the work energy theorem. The alternative to that is this formula over here, which is essentially the same. But obviously, when the body possesses both kinetic and potential energy, we have to augment that formula to obviously include the potential energy. So it's essentially the same thing. Is there any questions before I conclude the lecture? Monday will definitely be on campus if the taxi strike persists. But yeah, anyway, that's all for now. Any questions, students? Mr. Kochwe, Wendy, Charlie, Ms. Bierkes, Mr. Van den Kerk, Ms. Mpunguse, Bonani. Okay, so guys, I recommend you take a break. After that, Do the homework, push at least 5 problems of physics. I'm letting you know now, we have only August, September, October, 3 months left. Then you're writing finals in November. Only 3 months left. Then you can party the whole December. So I urge you to take your academic um, development or very seriously. So yeah, so make sure for the next 3 months you just sacrifice. You put in the work, your 3 hours a day. For my subject, I think you need at least 2 hours a day. For maths, maybe another 2. I'm not sure about computers and IMS. You definitely can do it. If I can do it, you can do it. Yeah, and that's basically all. But I'll see you guys next week, Monday, where we'll be doing Springs potential energy, like 3 examples, which we'll do. And then in the week, probably, yeah, but next week for sure, we're finishing energy. And in the following week, we're starting on topic 7. We're not doing topic 6. So if you want to work ahead, I'm telling you now. Okay, guys, all the best, and I'll see you.